So good afternoon, everybody. We're starting the afternoon session, which consists of one talk. And Matteo Mucciconi from University of Warwick will speak about a new approach to solvable KPZ models via correspondence with free fermions at positive temperature. Thank you.
Thanks a lot for the introduction. So the mic is working. Yeah, thanks for the invitation and for the possibility to give this talk. I will present this what we think is a new approach to solve to derive formulas for the KPZ equation, and in general for other solvable approximations of the KPZ equation that we found through correspondence with free fermions. So that's something hard in correspondence with something easy. It is based on collaboration with Takashi Mamura and Tomohiro Sasamoto, and on these three works on archive. So I will start with something that everybody knows, hopefully. So the KPZ equation we have is the standard model for growth of interfaces. We have here a profile that is going to evolve, and the evolution follows some smoothing, some lateral growth, and the randomness is given by the space-time white noise with the letter eta. As you know, this nonlinearity gives this equation issues to ill-posedness, but fortunately by now we know how to make sense of this equation. But nevertheless, I will not be caring too much about the well-posedness of this equation, but what I care is a very important feature of this equation, which is that starting from a certain nice initial condition, it is possible to write down exact solutions. So the initial condition that we will consider are particularly nice, what is called a narrow wedge initial condition. So imagine that we want to start this propagation of this random surface where the propagation starts from a single point. Imagine that this is a sheet of paper and there is a fire here, and the fire is going to slowly burning the paper, and we want to characterize the height function vertically. So this is not going to be a function, as you see, but so this is called narrow wedge because this is approximated to make it mathematically rigorous, make mathematical sense of this model with a narrow wedge picked at this point, indicated by this logarithm of the delta function. Anyway, so it is possible to write down exact formulas for this initial conditions, and as it was discovered in 2010, these exact formulas have a particular structure that you see in the screen. We have the Laplace transform of the KPZ equation plus shift, which is written as a Fredholm determinant, the expectation of this exponential function is written as the determinant, a Fredholm determinant of a product of two operators. One is the airy kernel, and the second one is this function here, which we call the Fermi factor, because it really looks like the Fermi Dirac distribution. So as it is clear from this formula here, there are relations between the KPZ equation and something on the right-hand side, which really reminds us of free fermions. But this is only apparent from the solution. No, it's dividing the e to, so this is a number, and no, it's not in the exponent, it's below. But you can put it in the exponent by redefining. Okay, but then we can also consider another geometry. Let's imagine that we have our piece of paper, and we, at the border of the piece of paper, we put some chemical compound, which is going to help or help maybe the combustion. Maybe this is gasoline, or maybe this is water. So the combustion is going to be slowed down at the edge. If we start the evolution with some fire starting from near the edge, then we expect that, that the evolution is going to be affected by the boundary, but only if we look sufficiently close to the boundary. Here, this chemical compound that we put on the edge is going to give a particular slope. This is how we model this situation. Is going to give a fixed slope to the height function at the boundary. And we want to ask if there is an exact solution. So the answer is yes. If there is an exact solution of this of the distribution of the KPZ equation near the boundary. This exact solution was found through many iterations, and it's what is written in the slide. So again, we have the expectation of this exponential function, the KPZ equation plus a shift t over 24 is equal to the Pfaffian, the Fredholm-Pfaffian in this case, of a 2x2 matrix kernel multiplied, which is some generalization of the Airy kernel, which appeared in the previous slide, times once again the Fermi factor. So once again we see some connection between the KPZ equation and free fermions. So this solution, I will say that the study of the half space problem is mathematically much more difficult than the study of the full space problem that I discussed in the previous slide. And people had arrived to this solution in many different papers. I think the problem is that produce a solution that works for any value of A. And I think that the most general solution was found by Denardis, Krejembring, Ledussal, and Thierry in 2020. So, but I will say that the papers in black they use certain techniques that make the derivation not totally rigorous. But on the other hand, the work by Barakan, Borodin, and Warwick and Wheeler, they use some techniques that make the derivation rigorous, but it's only for a particular value of A. So let's just recap what I just said so far. There are certain initial conditions that make the KPZ equation exactly solvable. And there are certain geometries that also depending on the geometry. The exact solution evoke some connection with free fermions, although we can only observe the connection from the solution. So we can don't have any hint from the KPZ equation to connect to some model of free fermions. So the question is, can we actually make this connection explicit and a priori? So can we derive these formulas by producing a connection with some model of free fermions? The second series of comments that I will make is that these solutions are usually derived through what is called the Bethe ansatz. There are some, this Bethe ansatz is, of course, many of you know, is a very powerful technique, but it requires some calculations, and sometimes this calculation cannot be made totally rigorous. So can we actually create a theory that is more elementary to arrive to these solutions, avoiding these complicated calculations? And the answer to this question will be yes, and it will be the content of the talk. So how do we actually solve the KPZ equation rigorously, like avoiding this irregularity of the KPZ equation? As it is known that this equation is irregular and it's somewhat divergent. So this is one issue to overcome. And what is done is that considers certain solvable discretization of the KPZ equation, which comes in the form of interacting particle systems. In this case, these models, for the most famous is the ASEP, clearly, and this model don't present any irregularity, and usually they depend on a structural parameter, which I indicate by Q, which let's foreshadow a little bit. This is going to take the meaning of temperature once this matching with free fermions that I will present later will be completed. These models all present a height function, regularized height function, which I call HQ, which in a certain scaling limit is going to converge to the height function of the KPZ equation. And so this recasts the question of characterizing the distribution of the KPZ equation into a probably more difficult question of characterizing the regularized height function of such solvable, exactly solvable models. So how do we actually go about solving this discretization of the KPZ? So the standard technique, these models all present certain common features, which I will explain through one example. So the example that I present here is an interacting particle systems, which takes the name of Q-push TASEP, and was introduced in 2012. And let me describe by the Markov dynamics. So this is a Markov process, and particles on the lattice. We assume that there are only finitely many particles on the lattice, and each particle possesses an exponential clock that is going to ring at some point. Let's assume that this clock rings with a certain rate governed by a parameter an, depending on the label of the particle. So when this clock rings, the particle is going to jump on its right, and this jump is going to trigger immediately a push. So this particle will push the particle immediately to its right, and this particle is going to feel the push, and this react accordingly, which means that it's going to jump to its right with some probability depending on the gap between the particle, exponentially depending on the gap between the particle, q to the number of sides. Notice that if the number of sides is 0, meaning that if two particles are actually neighboring, then the probability is 1. So in this case, the dynamics preserves the exclusion root. And this model, which, okay, you might like it or not, but it is, trust me, it's very simple. And in this case, the regularized height function is a very simple observable, which is the location of one of these particles. And in the large, when we take the number of particles to be very large and we scale Q accordingly, this is going to converge to in distribution to the solution of the KPZ equation. So a nice feature is that if we want to, now our goal is to approximate these nice initial conditions that are going to produce exact formulas. In this case, the regularization of the narrow wedge initial condition is given by this step initial condition, where we assume that the particle at the beginning are packed near the origin. And one thing is that there is some connection when we assume this initial condition. We can establish a connection between the probability distribution of a tagged particle, in this case n at time t, and a special probability measure, which is written in terms of the so-called Q-Whittaker polynomials. So these are special polynomials arising from representation theory that are connected to this model through there are various techniques to prove this identity, which I will not discuss, but the takeaway message is that certain initial conditions produce a match, a correspondence between the probability distribution of the regularized height function and certain probability measures of origin in integral probability in representation theory. So the Q-Whittaker measure was introduced by Borodin and Gorwin in their famous paper, McDonald process. So in this case, the quantity of the Q-Whittaker measure describing the location of the particle is the length of the row. Here, mu is a partition, which is a sequence of weakly decreasing sequence of numbers. And the first row of this partition describes the regularized height function. So a similar story is possible also for regularizing the models in half space. In this case, the model is almost the same, but we need to understand how to model the boundary condition. In this case, the geometry is different, And so we have to understand how to somehow mimic the presence of this boundary, which is going to affect the dynamics. So the way it's done is that, okay, we assume that there is this dynamics with pushing, but at some point, if we assume that there are finitely many particles, at the rightmost site, at some point, some particle is going to appear at each time step. And this particle, which is created at the rightmost site, is going to depend on a parameter A. And this parameter A, which is mimicking the boundary parameter, is going to tell us exactly the location of the new particle that gets created. Also in this case, the KPZ equation can be regularized by just observing at the location of a particle. So it's a very simple observable. In this case, there are also connections between this model and the special symmetric functions, measure of that can be written in terms of the special symmetric functions. If we assume very simple initial conditions, which is when the system is empty. So if the system is empty, we have to wait a certain amount of time and a new particle will be created. And so this particle will start traveling by itself. And at some point, a new particle will be created. So at some point, we will have two particles and they will start interacting using this push mechanism and so on. So this is how the system gets filled. And in this case, we have that the probability distribution of a tagged particle is described by another variant of the Q-Whittaker measure introduced later by Guillaume and Borodin and Corbin. So the message that I want to convey here is that we have recasted. So first we recasted let me use the whiteboard. So the first thing is that we want to study the KPZ equation. For some reason, this equation is irregular, so we regularize. So we study solvable discrete model. But now I'm taking another step, and I will study measures. Okay. From measures on partitions. So this is how this is the train of thoughts. And in this using this matching with measures on partition, the KPZ behavior is captured by this the first row on this measures on partitions. So one possible idea at this point would be to say that these special symmetric functions enjoy certain nice combinatorial properties, and so we just take advantage of these combinatorial properties. For example, it is known that they solve some recurrence relations, and one can try to extract formulas in this way. Although this works fine for models in full space, where we essentially obtain a regularization of the beta answers. In the right, so the time. This is some simplified model. I'm only looking at diagonal, and in this case, the time dependence is given by the number of variables. It's going to be A1, A2, A-T at some point. Okay. So there are this. One can try to regularize the beta answers using these formulas. Although it gets rather complicated for this other measure, because, like I said at the beginning, the models in half space are somehow more difficult to handle with these usual techniques. And so we can ask, like, are Pfaffian formulas only a feature of the KPZ equation, or do they exist even at this solvable level? This is a legitimate question. And to solve this question, we are going to pursue this goal: relate the mu1 in both of the cases with some natural statistics of determinantal or Pfaffian point processes, which originate from the free fermions. So now let's move to discuss a little bit on about the free fermions. I have the free fermions in two languages. Let's start with the language for physicists. And we are going to consider free fermions in one dimension. We have this notation, the Maya diagram notation. Here we have some Fermi C. Black dots indicate that the state is full, and the white dots indicate that the state is empty. And we use this notation. We have this n is going to give me this array of this configuration, where n is a list of numbers, n1, n2, n3, n-1, and so on, where n1 is equal, ni is equal to 0 if the site I is empty, and is equal to 1 if the site I is occupied. So it's what is called the Maya diagram. And we define the usual creation and annihilation operators that take a state, a configuration n, and creates a state at location k, or destroys a state at location a, if this is possible. And using this creation and annihilation operator, we can define some quadratic observables, which are, for example, the so-called fermion numbers, which counts. Okay, let's assume that we fix the origin here. Is going to count the number of particles at the right of the origin minus the number of holes at the right. Some natural statistics. This is the potential energy, which is going to count another statistics. Actually, this is the real energy, if we want to do some Hamiltonian dynamics. And well, there are some other nice observables that one can consider. And we will be interested in the expectations of a system where the initial state is given by exactly the Fermi-Dirac distribution. So we take each site occupied with well, we take this configuration occupied with this density. And we know by virtue of the weak lemma that if we consider a nice observable with these initial conditions, then this is going to have a nice determinant or Pfaffian formula expressions. Now let me switch to the more language for mathematicians by talking about, instead of talking about the Maya diagram and the creation and annihilation operators, I'm going to talk about the sure polynomials. So sure polynomials are these matrix elements of this what I call here the hopping term. These are sometimes called half vertex operators. Yeah, and in this case, the probability, the distribution of this Maya diagram is going to be written in terms of the sure measure. In this form here. So the probability of a part. So okay, so let me describe how to relate a Maya diagram with a partition. So we are going to find the location where the number of particles at the right is equal to the number of holes at the left, and then we are going to do the usual correspondence in writing the Young diagram in the Russian notation. But in this case, this is my Young diagram lambda, and the probability distribution of lambda is going to be given by this trace over this summation of the product of sure polynomials. So because the sure polynomial, so because this is just a reformulation of the language before, then this process here, lambda 1, lambda 2, and so on, is going to be a determinant point process. So are there questions? Sometimes the two languages are confusing. So this system here is called the periodic sure measure and was introduced by Borodin and studied even more recently by Beté and Boutier. And if we want to compute all the possible correlations, so this is the we are going to observe is a determinant process. So all we have to do is to compute the correlation kernel. And the correlation kernel is written in this double integral formula here. I don't want you to really pay attention to these formulas, but just take a look that they can be written all in a compact way. And so this is some model of free fermions. And maybe I didn't say that in this case I used the Fermi-Dirac distribution and q to the beta h and nu n. They were essentially the parameter governing the initial condition. But now I restated this parameter, and the q to the beta h is exp of beta h has become q, and exp of nu n has become this parameter t. There is also another nice, determinant point process that Pfaffian point process that one can consider by just cutting by using only one half vertex operator, meaning that we just basically cut the expectation in the middle. And in this case, this model was studied later. It's called the free boundary sure measure. Free boundary because essentially. There is only one boundary, and also in this case, this model in this case becomes a Pfaffian point process, and also in this case we can write down the correlation kernel for this Pfaffian point process in this form. Here we have that L of xy is this term here is going to be the 2-point function. Written is this discrete gradient, and written in terms of this contour integral representation. So now it seems that I am just introducing things, but let's clarify what I'm doing here. So before, at the beginning of the talk, I described two exactly solvable models in the KPZ class, some solvable regularizations. And I said that, if we want to study these solvable models, we have to study this probability measure on partitions. And if we want to study the problem in half space, we need to study this other probability measure. Then I introduced two other processes, interesting or not, but and they were determinantal and Pfaffian point processes. So, and now we come to the theorem that states that the models in the first line of this table are related in the following way. So if I consider mu1, which is my this regularization of the KPZ equation, and I shift mu1 by an independent random variable, the distribution of this new random variable is going to be equivalent to lambda1, where lambda1 is sampled according to this determinantal point process. And the same is true, there is this nice symmetry, also for the half space setting. If I sample mu1 according to this measure, and I shift this random variable by an independent random variable, what I obtain is the distribution of lambda1, where lambda1 is sampled according to this measure, which, as explained in the previous slide, lambda1 is, but lambda is going to be related to Pfaffian point process. So this is the theorem, and I'm going to move in the following minutes to explain what are the consequences of this theorem, which means that we are going to be able to solve these discrete models through this very simple matching, and then I will try to give a motivation for this correspondence to hold. But okay, I want to make sure that the statement is clear. So if there are questions, please let me know. Please. The distribution, okay. The distribution of chi is very simple. It's essentially geometric, a geometric random variable. So okay, in the the intuition is easier in the language of the KPZ equation. So in the KPZ equation, if you scale this distribution, this probability distribution here, you obtain a Gumbel random variable, and the Gumbel random variable plus another random variable is the Laplace transform of the random variable, okay, of mu1. So this is a Q deformation of a Gumbel random variable. Now, this is not an explanation, maybe. The explanation will come later, and it will be clear where this comes from. In a sense, this explains why the interesting observable is the Laplace transform. Okay. So let's draw some conclusions. So I think okay. Let me say something that I didn't say before. So this idea of connecting free fermions and KPZ models is not new. So this was apparent immediately from the formulas, and then there were a few papers. I think the first paper that actually put this statement down was by Dinle, Dussar, Majumdar, and Sher in 2015. There were also other works which are related to this part of the matching. By Borodin, Gorin, and other people, and some other work which are somehow related to this other part of the correspondence by Barakan and Borodin, Corbin, and Will. So there were some, although in this, so in the, let me just say why they are related and what is the issue with this. Previous works. So in these works here, in the work in 2015, as I said at the beginning, the correspondence was noticed only writing down formulas, not starting from the definition of the dynamics, but nevertheless was noticed. And in these other works, the matching between KPZ systems and free fermions is not as natural as I wrote here. In particular, in these works, the matching is between with the 1-point function of the KPZ equation and a non-local multiplicative observable of a system of free fermions. So in a sense, okay, there were previous works in this direction, but I think this is nice because it relates the 1-point function of solvable KPZ models with 1 point, well, the edge statistic of a system of free fermions. So these are some comments. Now let's draw some immediate conclusions. So if you want to write down the probability distribution of this observable here, okay, we shift it a little bit with some random variables which are independent, and this provides a matching with the determinantal point process, with the edge actually of a determinantal point process, and so the Fredholm determinant representation is immediate. In this case, we recall that we are talking about this solvable Q push stacep, and the probability distribution of the Q push stacep is written in this form of this Fredholm determinant. This is the same kernel that appeared before for the positive temperature free fermions. And we can take a limit, as I promised. There is a certain high temperature limit that takes the solvable discrete models into the KPZ equation. And so if we take a limit of these formulas, maybe you can imagine that this can be done. We recover some known result, which is that the probability distribution of the KPZ equation plus some deterministic shift plus some Gumbel random variable is written as a Fredholm determinant of the positive temperature Airy kernel. This is one result. But this is both, okay, this exact formula was not known, but other determinantal formulas were known, but this is a well-known result. So this is just to check that known results can be rederived. But now let's derive purely new results. As I said, the new results will concern mainly the half space problem, which is the most difficult one. And once again, we can write the distribution of this KPZ model in half space by shifting and using the correspondence with the free fermions. We can write it as a Fredholm Pfaffian. because this is going to be essentially the distribution of the edge of a system of free fermions. And in this case, the Fredholm-Pfaffian is exactly the same that you have seen before. So there is no special effect here. But now we can take the limit again. We can take this high temperature limit, which will transform our solvable discretization into the KPZ equation and recover some some characterization of the probability distribution of the KPZ equation at the origin. So we have that we are observing the spread of this surface of this interface, but we only look exactly at the boundary. And we write the probability distribution as a Fredholm-Pfaffian of a kernel, which is the limiting which is obtained as a certain limit of the kernel in the previous slide, where discrete derivatives become derivatives. So maybe this structure of the kernel is well, at least I liked it, but okay. And this kernel is some kernel which reminds a little bit the airy kernel. Okay, so this this formula here, because since there are poles here, so this Fredholm-Pfaffian formula is only true when A is bigger than -1/2. So it is possible to produce an analytic continuation of this formula, and the analytic continuation is going to be Fredholm-Pfaffian plus some correction times, sorry, not plus, times some correction. So this formula is valid for any value of A. Sorry, not this. There are formulas valid for any value of A, but this is only valid for A strictly bigger than -1/2. Okay. So how much time I have? 10 minutes, great. Okay, so this is probably the main result that I want to present, which is that we can solve basically without doing any calculation the KPZ equation by just borrowing results from known theories of free fermions and computing some limit. So they are related. So you should transform this sign using some angle summation, and then you should use this the usual integral representation of this sign, and then you do ABBA, and then you obtain your kernel with Alexander. The nice thing is that the same level of the addition summation for angles is becomes some identity of theta functions. It's okay. This your kernel is will be available also for Q models. It's very nice. So let me now give an idea of how. So far, I just presented the result. So there is basically no content. So I want to just give a proof of, give an idea of how this statement is proof, and respond also to the previous question, why this variable chi is entering the game. So the way we prove this correspondence here is by developing a bijection between some combinatorial objects I will define. This bijection, okay, before I go, this bijection, if you are familiar with combinatorics, is going to be a generalization RSK correspondence. So we have mentioned some free fermions. We have said that free fermions are imply the presence of sure polynomials, and so we recall that the sure polynomials labeled by these skew partitions are generating functions of semi-standard Young tableau. So what is a Young tableau? A Young tableau is a filling. So let's assume that this is my skew Young diagram. A semi-standard Young tableau is a filling of this white shape with in such a way that two numbers on the same adjacent on the same row are weakly increasing, and two numbers on the same column are strictly increasing. There are only finitely many ways to fill this shape. If I fix the maximum label that you can use, and the generating function is going to give the Schur polynomial. And then I mentioned that there is also another family of polynomials, which are the Q-Whittaker polynomials. Now, probably these are much less known than the Schur polynomials, but nevertheless, they are also interesting from various point of view, and they admit also this expression as a generating function over a certain other set of tableau. In this case, the set of tableau is what we call the vertically strict tableau, because in this case, the only condition, you have a shape, and you want to fill this shape by just keeping in mind that you can only, the numbers on the same column need to be strictly decreasing, but there is no condition on number on the same row. So this is equal, increasing, decreasing. So there is no condition. And I will put a weight on this tableau, and this weight is going to be called the intrinsic energy, which is different from the energy that appeared before. The one before was actually the Hamiltonian. This is not. This is just something called energy for some reason. And okay, and when we set this energy here is somehow telling us how far is the tableau from being semi-standard. Notice one very nice thing, that both generating functions are without minus sign, are of positive monomials. This will be important. So to understand why this chi, let me try to explain why this partition, this random variable chi is entering the game, and we take a look at the partition function of our measure. So we take our system of system of free fermions and we compute the partition function. In this case, if I state everything in terms of Schur polynomials, I am going to produce this identity here, which is sometimes which is called the Cauchy identity. In this case, the Cauchy identity takes this form where we are using this Q-Pockhammer symbol. Essentially, this is an infinite product over raising with raising powers of Q. So this is the partition function of my system of free fermions. And now let's look at the partition function of the Q-Whittaker measure. And okay, this is the partition function, and we see that in the right-hand side, we see something that we have seen already before. It's exactly this product of Q-Pockhammer symbols. And so these two partition functions only differ by a factor. But at this point, what we do, we recall that this factor here can be we can try to insert this factor here as a just by hand, just trying to desperately make the right-hand side look the same. And what I use here is that this is called the Euler partition function, the original partition function that Euler used to enumerate the number of partitions, and which says that the summation of Q to the number of boxes of a Young diagram is equal to this. And so now I have in the right-hand side, in the right-hand side, I have the same quantity, but in the left-hand side, I have greatly different quantities, which I want to relate. And notice that if I block the partition nu, which has appeared now, if I block the size of its first entry, then the probability distribution of the length of the first entry is equal to a certain number is equal to exactly this random variable chi. So this is, if you want, one reason why this random variable chi enters, because I want to make the partition function look the same. And now I use the combinatorial formulas that I have that we have seen on the previous slide. So to expand the left-hand side of this partition function identity in terms of positive monomials, and I do the same also for this Q-Whittaker measure. In this case, there is a new. Okay, I'm using this expansion of the Q-Whittaker polynomials using this vertically strict tableau, I'm using the intrinsic energy function. I am using this partition nu, this fudge factor, and I am also using a new quantity here, which is kappa, which comes from a combinatorial expansion of these terms b mu. So if we only take a look at the right-hand side now, we have a monomial expansion of this object here and a monomial expansion below. So the idea is to match each monomial of the two expansions. So the first summation only depends on a pair of tableaux P and Q of the same shape, while the second expansion depends on a quadruple and a list of number k, kappa, which is enumerated here. I'm not explaining exactly where this comes from, but it's a combinatorial expansion of these terms b mu. And finally, we have these partitions here that I inserted at the beginning. So this is the idea. And okay, now I don't have time to explain why this bijection is produced, but yeah, this is the content of essentially this is the proof of the correspondence. And if we develop, I mean, the bijection that we have found has some nice properties. In particular, the nice property is that if lambda is the shape of a P and Q and mu is the shape of V and W, then lambda 1 is going to be equal through this bijection to mu1 plus nu1, which explains the terms chi in the correspondence between KPZ models and the free fermions. And okay, recombining the generating functions, but blocking the length of the first row, we find this identity here, which is and setting P equal to Q, so which means taking some symmetry of this bijection, we recover essentially the expansion in terms of symmetric functions of our correspondence between half space KPZ models and Pfaffian point processes, essentially. So the takeaway message here is that we can prove the correspondence using a bijection, and the symmetries of this bijection are going to imply this nice symmetry between the half space model and the full space model. So let me conclude. So we have established this correspondence between this difficult thing to study, which is essentially the KPZ equation, and something very simple to study, which is the free fermions at positive temperature. And so some achievements, immediate achievements of this correspondence are formulas which are derived just almost mindlessly. You don't have to think a little bit. You have to just copy the formulas that you find on that comes from the free fermionic theories. And there are still some. So this is nice, but there are still some iffy points, some things that I'm not still a little bit working on. We are working on, and that is to first of all to possibly refine this correspondence between one point function of the KPZ equation and edge statistic of the free fermions to include some multi-point expectations. This is certainly contained in the bijection that I did not explain, but some work needs to be done. And another thing is that I should probably it would be better not to go through all of this difficult discretization and create something maybe more nice to describe really the correspondence between KPZ equation and free fermions starting from the KPZ equation and without going to all of this discretization. Okay, then thank you very much. And
thank you very much. We have time for questions.
Can you say something also about the lambda 2 and mu 2? Or?
So there are, okay. So if okay. So in this bijection, there are formulas that relate the shape of which is essentially mu2, the shape of the second row of V and W, with the second row, or with not the second, with some other statistics of this determinantal point process. So these are the somewhat intricate functions. So, but there is some relation.
Other questions? Yes, but just a moment. For the record.
Like in the zero temperature case, can you do something away from the boundary? And what on the second, what this multi-point observable mean? Do you mean a different position or what?
I believe that. So I believe that this the bijection this bijection here will this bijection will be able can describe the 2-point function at the same time. So so this is the type of multi-point observable that I'm looking for, like h x1t, h x2t. In order to do so, which essentially answers also your other question about the off-diagonal points, one should be able to refine. In my opinion, one should be able. I think one should be able to refine this proof, where one takes somehow the V and W to be skew. Some proof of the skew Cauchy identity using this correspondence. I don't know how to do this. So.
Any other questions?
So I have another comment. So not necessarily you have exact formulas, but probably maybe you can bound the x1 and x2 and take a limit, and this gives exact formula by bounding, and so this is another idea.
Can you consider any other initial conditions? I'll just give it. Say maybe you can start with invariant distribution with Wiener process for KPZ and independent from the noise, and then.
Yeah, this is possible. It is known that if you have a solution that holds for if you have any solution, exact solution, then there are ways of sort of letting that solution reach a stationary state, and keeping some formulas, and this is going to give you formulas also for the stationary state. There are some algebraic tricks to do this, but yeah, essentially what one can get is some like you say, some Brownian some stationary initial condition. This is
and solve equations starting from it.
Yes.
With exact formula.
Yeah, you are going to get exact determinant and Pfaffian formulas for this stationary initial conditions.
It was some question here. Philip? No? No, there are no further questions. So then let's thank our speaker again. And